Here we're going to see how each of the 16 Vedic Math Sutras can be used in division. So these are the 16 sutras, and we're going to start with vertically and crosswise, Urdhva Tiryag Vyam, because that's the sutra for the general division method in Vedic maths. By this method, Tirthaji shows that any number can be divided by any other number in one line. So for example, if you want to divide 3210 by 731, you can do that in one line, and the trick is to only use the first figure as a divisor and adjust for the others, or sometimes we may use a two-figure divisor if it's a small one. So this is how we would work out that particular division, and there are some remainders, and the answer is on the bottom line 4.16, and that's vertically and crosswise division. Tirthaji covers this in chapter 27 of his book, and you can do algebraic divisions this way too. But sometimes the divisor is a little awkward and we need to adjust the numbers that we're working on to make them work well with the vertical and crosswise division. And so one might ask, what are the techniques that we can use to alter the given division, or what alternative division techniques are there? Tirthaji also shows a method called argumental division, in which he takes the multiplication method of multiplying algebraic expressions and reverses that so we can do division, and that also actually can be used for dividing numbers. So if we wanted to divide 1904 by 56, we're really asking what digits need to go here to multiply 56 to give 1904, and by reversing vertically and crosswise multiplication we can do that. And Tirthaji covers this in chapter 6. So that's vertically and crosswise. I'm not going to go through these in any detail. There's a lot of other things to show in the time available. But vertically and crosswise, or the Urdhva Tiryag Vyam Sutra, is the main sutra for general division. Then there are two further methods, one where divisors are just below the base, and one for where they're above. So if they're just below the base, it's called all from 9 and the last from 10, because if we want to divide, say, 1234 by 988, we notice that our divisor is close to a base of 1000 and is 12 below 1000, and so we apply this method which Tirthaji gives us in chapter 4. So we use the deficiencies from the base, so 1, 2, and they are obtained using all from 9 and the last from 10. Nikilam Nawatash Charamandashata, and that's how it goes. That's the setup. Then transpose and apply is used where the divisor is just above a base. For example, 112 is just above 100. The Sanskrit for that sutra is Paravatya Yojayit. That's in chapter 5 of the book, and that's how it works. So the answer is 11.02. And this also Tirthaji shows is used for algebraic division as well. Now let's start at the top of the list by one more than the one before, Ekadikena Purvena. Tirthaji shows how we can use this for working out recurring decimals. So for example, for 17 over 19, this is covered in chapters 1, 26, 28, we use the number which is one more than the one before the 9, so 1 more than 1 is 2, so we divide by 2. And 2 into 17 is 8 remainder 1, 2 into 18 is 9, and so on. It's very nice, and it can be extended in various ways. And divisibility too, we can do with this sutra. Now we'll just go down the list in order. If the Samuccaya is the same, it's 0. Shunyam Samya Samuccaya. And this is actually used when we're cancelling fractions. Suppose we got 10 over 15, 10 divided by 15. We note that both of these numbers have got a factor of 5 in them. So that is the same, that factor of 5, and therefore it's effectively 0, and so we get 2 over 3 when we cancel it out. And a reverse application of that would be in getting the decimal for, say, 7 over 229. If you know that 229 multiplied by 131 is a very special number, then we can get this very easily. We simply multiply by 131 over 131. It's the same, so we can do that. 131 over 131 is just 1. And what we get is 917 over 2 followed by 4 nines, which means that we can get the answer very easily by simply dividing by 3, and we divide 3 into 0917, and because there are 4 nines there, we get the answer 4 digits at a time. If one is in ratio, the other is 0. Anurupye shunyam anyat. And this comes up when we've got a division like this, a quadratic divided by a linear term, in which it actually cancels out because x plus 2 is a factor of the numerator. And so we can say 1 is in ratio, the x plus 2 is in ratio, and therefore the remainder is 0. And the same thing applies in the numerical case as well. By addition and by subtraction, sankalana uyawakalanabiam. First of all, a reminder about adding fractions in the Vedic system. If we want to add a fifth and 2/7, for example, we cross-multiply for the numerator, so we have 1 times 7 and 2 times 5. 7 and 10 is 17, and we multiply horizontally. 5 times 7 is 35. So crosswise gives us a 17, and then horizontally gives us a 35. So given a fraction like, say, 23 over 76, one technique at our disposal is to split it up. A fraction can be split up into 2 fractions. Now if you notice that 76 has got factors 4 and 19, then we can think of it as being the sum or difference of 2 fractions with denominators 4 and 19. Can we make the numerator 23 out of suitable additions or subtractions of these crosswise products? And in this case it's very easy because 4 and 19 is 23. So if we were to put 1s there, we would get 19 and 4 is 23 over 76. So this is the same as that. And this is a bit easier because instead of having a divisor of 76, which is a little awkward, all we need to do is to add up 0.25 and the decimal for 1 over 19, which is easy to get. And this can be extended. Let's say we've got 34 over 76. How can we do this? How can we find numerators with a plus or minus here in order to get that 34? Well, a little thought may show us that 34 is actually 4 below 38, which 38 is 2 19s. And so that gives us the clue that we can do this, 2 over 4 minus 1 over 19, because that would give us 38 minus 4, which is 34, and 76 underneath. So we can get the answer more easily here by working out 0.5 minus the decimal for 1 over 19. A slightly different application here. You may notice that 30 and 58, well, the numerator is approximately half of the denominator, and so we might split it up into 29 plus 1.34, like that. 0.5 then plus this fraction, and we might think that's easier to work out than that is. By the completion or non-completion, Purana Puranabhyam, this we would use if we had a fraction which was close to a unity of some kind. So in this case, this fraction is close to 1, and we can think of it as 1 minus 3 over 433, and so 3 over 433 is easier to work out than that. And so we'd work out this and take the answer away from 1. And 13 over 19, similarly, we can think of 2 whole units that this is close to, and so 2 plus 1 over 19. that's how we can use that sutra for division. Differential Calculus, Chalana Kalanabhyam, given in chapter 22 this. So this is Tirtji's method. We start off with some cubic and we want to factorize it. And we see first of all that it's divisible by x minus 1, because if you put x equal to 1 in here, you simply add up the coefficients and you get 0. So x minus 1 is a factor of that. And we can use this sutra to find out if there are any repeated factors in that cubic. What we do is differentiate it to get this, and test again to see if x minus 1 is a factor, which it is, because 3 minus 8 and 5 is 0. So this is divisible by x minus 1, and therefore this cubic is divisible by x minus 1 squared. It's a repeated factor. And that helps us to factorize the given cubic, because it will be equal to that repeated factor multiplied by some linear term, which we can easily get, because here we've got x cubed, here we've got x squared when we multiply out, so this must be x. And at the end here we've got minus 2, and this will be a plus 1 when we multiply out, so this must be a minus 2. And so we factorize that cubic using differential calculus. By the deficiency, Yawadunam, this is given by Tirtji in chapter 4, and we know how we can divide by 9 very easily using the fact that 9 is 1 below 10. And here it goes, we put the 9 there and the dividend here, then we bring down the 1. 1 and 2 is 3, 3 and 3 is 6, we get 13, remainder 6, using the deficiency. If the divisor had been 8, then we would be doubling before we add on, because the deficiency is then 2. And similarly, 11 is 1 over 10 rather than 1 below as we had here. So that works a little differently. We bring down the first one, and then we take that 1 from 2 to get 1, we take that 1 from 3 to get 2, we take that 2 from 4 to get 2. And we can also extend this a bit further. Here we've got 98 as a divisor, so the deficiency is 2, because 98 is close to 100. We can work in pairs of figures. So the dividend can be written as 1, 2, 3, 4, 5, and we bring down the initial 1, and we add it to the 23, but we double it first because our deficiency is 2. So 2 and 23 is 25. We double that, 25, and add it to the 45. 50 and 45 is 95. We get 125, remainder 95. Specific and general, Vyashti Samashti. Tirtji only shows one example of the application of this particular sutra in the solution of a certain type of biquadratic equation, and he explains that he actually uses the average in order to do it. So we're going to be using the average in order to carry out some division, or rather divisibility. Is 13578 divisible by 73? Say. Well, because this number is even, we can divide it by 2 and ask if 6789 is divisible by 73. Because if this number is divisible by 73, then dividing it by 2 won't change that, and if it's not divisible by 73, then that won't be changed either by dividing by 2. So we get this number, and we note that this is now odd. But I want to keep dividing by 2, so what I'm going to do is to add that 73 there onto the 6789, which will give me an even number, and then divide by 2. And adding the 73 on will not change the divisibility or non-divisibility of the number by 73. And what I'm doing then, by adding 73 on, getting an even number and then halving, is finding the average of 73 and 6789. So that's what I do repeatedly. I add 73 on and halve it to get the average. I've got an odd number here, so I'll add 73 on again and halve it, find the average. Now I've got an even number, so I divide by 2 and keep dividing by 2 until I get an odd number. And now I notice that I've actually got 3 73s, and so this is divisible by 73, 13578. Or you can repeat the process as many times as you like. Find the average of 73 and 219 until it becomes more obvious that 73 is a factor. The remainders by the last digit. This is a technique given by Teertje in chapter 25, and we can illustrate it by thinking about 1 divided by 7. And here's the actual division if you were to do it out in detail. 7 into 1 is 0, remainder 1. 7 into 10 is 1, remainder 3, and so on. So we get a series of answer digits here and a series of remainders here. So those are the remainders we're going to work on, and we're going to get the answer by using the remainders and the last digit of the recurring decimal, which is 7. And the remainders are easy to generate because once we get a ratio at the beginning, here we've got 1 to 3 ratio, that ratio continues throughout. So if we got a 1 here and 3 here, we'd expect a 9 here. But we've got a 2, and that's because the 7 has been cast out of that 9 to leave you with 2. Then we multiply it by 3 again. We get 2 times 3 is 6. 6 times 3 is 18. We cast out 2 7s, and that leaves us with 4. And then 4 times 3 is 12. Throw out a 7, we're left with 5. 5 times 3 is 15. Throw out 2 7s, you're left with 1. So this is the remainder cycle. And now we can use the last digit, the 7, in two ways. We can either divide from the left or multiply from the right. If you divide from the left, then you say 7 into 10 is 1, and ignore the remainder. 7 into 30 is 4. 7 into 20 is 2, and so on. Or working from the other end, we can multiply by 7. Multiply the remainders by 7. 1 times 7 is 7. 5 times 7 is 35. Ignore the 3 and just put down the 5, or just put down the last digit. 7 4s are 28. 7 6s are 42. Just put down the 2. 7 2s are 14. 7 3s are 21. So this is a nice technique from chapter 25 of the book. The ultimate and twice the penultimate. So puntia dvayamantyam. And this is used when we are testing for divisibility by 4. So for example, if we want to know if this number is divisible by 4, we apply the sutra, the ultimate and twice the penultimate, which means we take the 4 at the end, that's the ultimate, and twice the one before it. The 4 plus twice the 7. We get 18, and 18 is not divisible by 4, so this is not divisible by 4. But also, this gives you the remainder as well, because once you've cast out your 4 4s from there, you're left with the remainder of 2. And similarly, if it was 575 divisible by 4, you would do the 5 at the end, and twice the 7. 19. So the answer is no, but the remainder is going to be 3. Because once you take 16 away, you're left with 3. For 576, we do 6 times twice 7. We get 20, and 4 divides into that, so the answer to the question is yes, and the remainder is 0. And this can be extended to divisibility by other powers of 2. For example, if you want to know if this is divisible by 8, we take the last figure, the ultimate, the 6, twice the 7, and 4 times the 5. Twice 5. So you have 6, twice 7, and 4 times 5 comes to 40. 8 divides into 40, therefore 8 divides into 576. And the same applies here if we had ended up with 41, which it would be if we had 577. We could say that the remainder is 1, because once we've thrown out all the 8 we're left with 1. By 1 less than the one before, I kan ju neina porwaina. Couple of reminders here. First of all, T2G shows a nice method for multiplying a number by a series of 9s. So for example, if you had 869 times 999, you reduce this number by 1 less. So you get 868. And then you apply the Nicolam Sutra, all from 9 and the last from 10 to the 869, and put down 131. So that's the answer. Reduce this by 1 and apply the Nicolam Sutra to that for the other half of the answer. The other reminder is that if we had a number like 531, which we're dividing by as many 9s as there are digits in that number, then it's very easy to put down the answer. It's just the 531, but recurring. 531, 531, 531. So let's take an example, how we can use 1 less than the one before in division. 869 over 1001. We're going to multiply the top and bottom of this fraction by 999, because that will give us a series of 9s underneath, and we can use this method here. So multiply the top by 999 using this method, just like that, and then the bottom just becomes 6 9s. So using our 1 less method, we can multiply those numbers on the numerator to get this, and then we can write out the recurring decimal. It's just the numerator repeating over and over. Another example, 17 over 77. We need to get 9s in the denominator for this method to work. And so we multiply the top and bottom by 13. That gives us this fraction here. And then we multiply by 999 again, because it's now a bit like this one here. And we get this. And so that gives the answer 220779. So the key is really to just get 9s in the denominator if you can possibly do it. And here's another example. 10101 is in the denominator, but if we multiply by 99, we get a series of 6 9s. And we know how to multiply 59 by 99 by this method up here, and so that's what we get. We put in a couple of zeros, so we got as many figures in the top as in the bottom, and then we can write down the recurring decimal like that. The product of the sums, Gunita Samuccaya. This is given by T2G in chapter 7. Suppose we want to divide this cubic by this linear term. We know the answer is going to be a quadratic. And we know the first and last terms because x cubed divided by x is x squared, and 6 divided by 2 is 3. We just don't know the middle term. But we can use this sutra to work it out. Because according to this sutra, the sum of the digits here, the sum of the coefficients here, is equal to the product of the sums of the coefficients here and here. And that means that we can simply add up the coefficients here and here, divide them, and that will give us the sum of the coefficients here. Here the coefficients add up to 24. Here they add up to 3. 24 divided by 3 is 8, so these coefficients must add up to 8. 1 something and 3 adds up to 8. It must be 4, and we get x squared plus 4x plus 3. Finally, all the multipliers, Gunaka Samuccaya. And this is a technique which is pretty obvious really, but it works sometimes if your divisor can be split into factors. For example, 36 has got lots of factors, so we can divide this in steps. 36 is 2 times 2 times 3 times 3, or if you like it's 2 times 2 times 9. And so we could divide by 36 by dividing by 2, and then dividing by 9. And I've chosen 9 rather than 3 times 3 because it's easy to divide by 9. So we divide this by 2, 1402. We divide by 2 again, 701. We use our division by 9 method. We get 77 remainder 8. So that's it. That's how the 16 sutras can be applied in various types of division. And as a challenge, I'd like to suggest maybe there are other topics in which you could find how the 16 sutras apply. For example, multiplication devices. Can you find 16 multiplication devices, one for each of these 16 sutras? Thank you.